Hello again, everybody. This one's going to be an introduction to numerical linear algebra as seen in a first semester numerical analysis class. So far in the class, we've talked about approximation of functions with Taylor series. We've talked about numerical algebra and root finding techniques. And we've talked about numerical calculus, things like numerical differentiation, integration, maybe some optimization, things like that. The next order of business here is to talk about numerical linear algebra. So the primary questions in numerical linear algebra are not necessarily to solve problems that you can't do by hand, because if you think back to calculus, like numerical integration, for example, or algebra, a lot of those are things we couldn't do by hand. Linear algebra, you can often do by hand given enough patience, enough care with your arithmetic, and a lot of time. But the algorithms, things like row reduction or things like finding an orthonormal basis for a vector space, things like that, they're really tedious. So we're going to look at things like solving systems, approximating solutions to systems, doing eigenvalue, eigenvector computations. But we're going to be looking at doing those in a computationally efficient way. That's where numerical linear algebra is really pretty amazing. And the cool thing about numerical linear algebra is that people have been at this for many, many decades now, and we have algorithms that are provably optimal. In other words, you can prove mathematically that you'll never be able to find algorithms that are any better. And these are built into most pieces of software like Python or MATLAB or Mathematica or things like that. So I'm going to show you a couple examples, right? So fast algorithms. If we were to solve a system of equations, right? So you got a square system of equations, you have a matrix, you have a right-hand side. What you would normally do by hand is you would augment those and row reduce. And row reduction is a very tedious computation. Now there is row reduction built into, say, Python or other tools, but there are way faster algorithms. So as you've seen in these other videos, you can ignore this code for right now. What I've done is said, I'm going to build a system. I'm going to have Python go and do the row reduction problem, and then I'm going to have it do the numerical linear algebra routine to solve the exact same problem. So for a 5x5 system, right, it took almost no time. What is it, tens, hundreds, thousands, 5 thousandths of a second to row reduce that? You're not going to notice that time. And on the same exact system, the numerical linear algebra routine was actually an order of magnitude faster, but there's no way that us as human beings would even notice that difference. 10 by 10, 2/100ths of a second for row reduction, and we're still talking in the order of 10 thousandths of a second for the numerical linear algebra routine. Well, let's ramp this up a little bit. What if we did like a 50 by 50? This is almost now 2 seconds to solve by row reduction, and we're still on the order of 10 thousandths of a second on the numerical linear algebra routines. In other words, as we ramp up the size of our matrices that we're trying to do, or we're trying to use for a linear solve, row reduction is bogging down. It's taking longer and longer and longer to do, whereas the numerical linear algebra routines are exceedingly fast, like really, really fast. On a 200 by 200 system, it took my machine 1.5 minutes to actually solve by row reduction, and it still took 1/1000th of a second with the numerical linear algebra routine. This should be enough to tell you I need to learn these new linear algebra routines. I don't want to wait forever to have my computer or to try and do it by hand for row reduction. Okay, so that's one thing we're going to do. We're going to build several algorithms for that. Now, the last one I'm going to show here is just a quick little application. You may have seen this application before. Let's presume that these nodes on this graph are, say, web pages. And the arrows are links from one web page to the other. So like web page number 1 links to 2, 2 links to 3, 3 links to 1 and 2, and 5, and so on. Now, finding the most important of the web pages in here actually turns out to be an eigenvalue problem. But it actually turns out to be a numerical eigenvalue problem if the graph were to grow very large, because all we would be interested in is the largest eigenvalue and the associated eigenvector. And there's a numerical routine that does that really quickly. This doesn't have to be web pages. These could be, say, soccer players. and soccer player number 1 passes to soccer player 2, we might put a weight on this edge now, like 50% of the time or something like that. 2 passes to 3, 3 passes to 1 and 2, and so on. And we could use this numerical eigenvalue, eigenvector routine to determine who the most important player is on the field. And that is absolutely a computational or a numerical eigenvalue problem. This is actually similar to what Google uses to rank your web pages as to which web page you see first, second, third. That's a numerical eigenvalue problem. So this is what we're going to see, or at least part of what we're going to see in numerical linear algebra.